Big Bang Theory, the most widely accepted explanation for how the universe began. It says that around 13.8 billion years ago, everything in the universe was squeezed into a tiny, hot, and dense point. This point then suddenly expanded very quickly. This expansion was not like a bomb exploding, but more like space itself growing in all directions. As the universe expanded, it began to cool down. Tiny particles formed, which later joined together to make atoms. These atoms grouped to form stars and galaxies. Over a very long time, planets like Earth formed too. Scientists support this idea with evidence like galaxies moving away from us and leftover energy in space called cosmic microwave background radiation. The Big Bang Theory does not explain what caused the beginning, but it helps us understand how the universe grew and changed over time. Steady state theory. This is an alternative idea to the Big Bang Theory about how the universe began and evolved. It was proposed in 1948 by Fred Hoyle, Thomas Gold, and Herman Bondi. This theory suggests that the universe has always existed and looks the same in every direction at all times. As the universe expands, new matter is continuously created to keep the overall density the same. This means that galaxies move apart, but new ones form in the gaps, making the universe appear unchanging over time. The steady-state theory does not have a beginning or an end. However, this idea lost support when scientists discovered cosmic microwave background radiation in 1965, which is leftover energy from a hot early universe, supporting the Big Bang Theory instead. According to NASA, this radiation is strong evidence against the steady-state model and supports a universe that had a definite beginning. Multiverse Theory. The idea that our universe is just one of many universes that exist. These other universes could have different laws of physics, different types of matter, or even different versions of reality. The multiverse idea comes from several areas of science, including quantum physics, string theory, and cosmic inflation. One version suggests that after the Big Bang, parts of space kept expanding, creating bubble-like universes with different properties. Another version comes from quantum mechanics, which says every possible outcome of a decision or event could create a new universe. While the multiverse theory is interesting, it is still a topic of debate because it is very hard to test or observe. Some scientists support it because it could help explain why our universe seems so perfectly suited for life. Cyclic Model. This theory suggests the universe goes through endless cycles of expansion and contraction. Instead of starting from a single Big Bang, the universe is born, grows, collapses, and is reborn again in a repeating pattern. Each cycle can last trillions of years. This idea removes the need for a beginning or end of time. Some versions involve two universes colliding over and over, creating new Big Bang-like events. The theory is based on ideas from string theory and cosmology. While interesting, it is still being explored and lacks the strong evidence that supports the Big Bang. String theory and brain cosmology. String theory is a scientific idea that tries to explain everything in the universe by suggesting that the most basic building blocks of reality are not tiny particles, but tiny vibrating strings. These strings are incredibly small, much smaller than atoms, and they vibrate in different ways to create different particles, like electrons, quarks, and photons. Just like a guitar string can make different notes depending on how it vibrates, these strings make different particles based on their vibrations. String theory also says that the universe has more dimensions than the three we see around us: length, width, height, and time. In fact, string theory needs up to 10 or 11 dimensions to work properly. Most of these extra dimensions are thought to be curled up so small that we can't see them. One of the biggest goals of string theory is to connect two major ideas in science: general relativity, which explains gravity and the large-scale universe, and quantum mechanics, which explains tiny particles and forces. These two theories don't currently work well together, but string theory might be the key to combining them into one complete theory of everything. Physicists at CERN have used the Large Hadron Collider to look for signs of extraspatial dimensions, which are a key part of string theory. One approach to test the existence of string theory is to look for unusual particle collisions that could suggest energy is leaking into another dimension. This might show up as a missing energy in the detectors. In 2015 and beyond, several experiments at the Large Hadron Collider focused on this idea. One study published in Physical Review searched for signs of gravitons disappearing into extra dimensions. They didn't find any evidence, but they were able to set limits on the size and properties of those dimensions. Anthropic Principle. This principle is the idea that the universe appears perfectly suited for life because we are here to observe it. If the conditions of the universe were even slightly different, like the strength of gravity or the charge of an electron, life as we know it couldn't exist. The weak Anthropic Principle says we observe a life-permitting universe simply because we exist in one. The strong Anthropic Principle goes further, suggesting the universe must have properties that allow life to arise. Some scientists connect this to the Multiverse Theory, saying if many universes exist, it's not surprising we're in one that supports life. Critics argued the Anthropic Principle doesn't truly explain anything, but others find it helpful for understanding why the universe's physical laws seem so finely tuned. It remains a debated concept in both science and philosophy. Loop quantum cosmology. Loop quantum cosmology is a theory that tries to explain the early universe by combining quantum mechanics and general relativity. It is based on loop quantum gravity, which says that space and time are made up of tiny loops, like a woven fabric. Instead of being smooth and continuous, space is made of very small, discrete chunks. In loop quantum cosmology, the universe didn't begin with a singularity like in the Big Bang. Instead, it suggests there was a quantum bounce. This means the universe was once shrinking, reached a very small size, and then bounced outward into expansion, like a ball bouncing off a wall. This model avoids the problem of infinite density and temperature at the start of the universe. It offers a possible explanation for what happened before the Big Bang. While still theoretical and not yet proven, loop quantum cosmology gives scientists a new way to think about the universe's beginning. Holographic Principle. The theory in physics that suggests everything in our universe, including space and matter, might actually be described by information stored on a distant, two-dimensional surface. It's like how a hologram on a credit card looks 3D, but is made from a flat surface. According to this idea, our three-dimensional universe could be a projection from information on a two-dimensional boundary far away. This principle comes from black hole physics. Physicist Jacob Bekenstein found that the information content of a black hole is related to the area of its surface, not its volume. Later, Stephen Hawking and others showed that black holes store information this way, leading to the idea that maybe the whole universe does too. While still theoretical, it helps scientists explore how gravity and quantum physics might connect. Simulation hypothesis. The idea that our entire universe, including everything we see, feel, and experience, might be an artificial simulation, like a very advanced video game. It suggests that we could be living inside a computer program created by a highly advanced civilization. This idea became popular in modern philosophy and science through a 2003 paper by philosopher Nick Bostrom. He argued that at least one of the following must be true. 1. Civilizations never reach a level where they can run realistic simulations. 2. Advanced civilizations choose not to run simulations. Or 3. We are almost certainly living in a simulation. If number 3 is correct, it means that the beings running the simulation could observe or influence us, and our entire universe could just be data. Supporters point to how our universe follows precise mathematical laws, much like a computer program. Some scientists also find it strange how certain aspects of quantum physics, like particles changing when observed, could resemble how computer graphics only load when needed. Critics argue that the hypothesis is impossible to test or prove, which makes it more of a philosophical idea than a scientific one. Others say it raises more questions than answers, such as who created the simulation and why. Despite the lack of evidence, the simulation hypothesis remains a popular and intriguing idea in both science and pop culture, with some researchers even proposing ways to look for glitches or patterns that could hint at a simulated reality.